Hi, everyone. Happy Monday. Let's see here. We are in the midst of a unit called OFDM, but we have so far only been talking about equalization in channels. Before I launch back into the slides, I should let you know that there is an addendum to the slide set. It's called OFDM2. It's available on Canvas. It's just 4 additional pages of notes. So, and I hope we'll get to those today. All right. Any questions that have come up since our last chat? All right. We had talked about zero forcing equalization, and then we had moved on to MMSE equalization. Zero forcing equalization is fine, but if you have, a channel in which there are spectral nulls in the band in which you're trying to communicate, then you end up amplifying the noise because you've ignored it, basically. You can accomplish zero intersymbol interference, but you can lead to drowning yourself out if there are spectral nulls or even just low spots in the spectrum of the channel. So an alternative for that is let's try and eliminate ISI and the noise effect kind of combined. As you might imagine, you won't get as good ISI nullification, but you will get better noise nullification. So the idea is that maybe we can do something better overall. And the idea behind a minimum mean square error equalizer is that we're trying to take the data that we are receiving, which I'm calling Z of n, and pass that through an LTI filter, possibly with a time delay, the output of which should be our best guess, or should allow us to make our best guess about what was sent. And so I've defined the error in this optimization problem as the difference between the signal D of n and the actually sent symbol from U time steps ago. And again, U, if you don't like it, you can get rid of it. You can set it equal to 0. And I don't think you lose anything until the very last bit in here. But the idea is that you might want to allow yourself some delay so that you can end up making a better decision. So let's allow the delay to be a variable which we can optimize over. That's kind of where we're headed. Okay, so we've got the error defined. We've got the mean square error defined. And now we're going to try to minimize it. Minimize it how? By choosing filter constants for our equalizer filter, which I'm calling capital F of C. All right, that wasn't so bad. It was a weekend off, and now we're back where we were on Friday, right? Right. So in that process, the way to optimize for, or one way to optimize for the minimum mean squared error is to recognize that if you have the minimum, that means that the error has to be perpendicular to the data. Is one way this is commonly phrased. So I'm looking on slide number 9. And so I'm using the orthogonality principle of optimization to make this statement that the error should be perpendicular to all of the received data. And this statement is true for all past received data. Okay. I was trying over the weekend to think of a better way to convince you of this, because I think that I probably didn't do a great job. And spoiler alert, I didn't come up with a great solution. But the idea is that if I have just 2 data pieces, so let's just say I have Z of 0 and Z of 1, then those 2 can be thought of as being on a plane. So here's Z of 0, and let's say here is Z of 1. And what I'm trying to do is I'm trying to pick the best spot in this plane to get to something that's not in the plane. And it's not in the plane because it's what's going to be sent corrupted by noise. And so if I'm trying to get to maybe somewhere up here, then this is going to be my error signal. So drop this guy down here. So then your best estimate is going to be this, call it D1 and D0. And because you can only live in the plane where your data suggests that you can be, then these two, if I had picked a different D0, so if I'd picked D0 prime, then the error vector would be longer. So here's error prime, and here is error. And you see that if I pick D0 prime or D1 prime anywhere else in the plane, then I get a longer error vector, a larger error magnitude than if I had picked the two here that give me orthogonality in both directions, right? So I've got two right angles here. Now, as soon as you knock this up to more than 2 dimensions, it becomes really difficult to conceptualize, especially it's difficult to draw. But the idea is that we're always living in some kind of subspace. Here it's a 2-dimensional plane inside of a 3-dimensional space. We're always living in some kind of subspace, and the point that we're trying to estimate is in general outside of that subspace. If there's no noise, then this point, this perturbed point here, is going to be in the plane, and we can get there precisely. So that's great. And I think what you would get is you would get zero forcing if you had no noise. Because then if there's no noise to account for, then the best you can do is 0 ISI, which we did with zero forcing. But in the presence of noise, you're going to get popped out of the plane and into a new dimension. Therefore, the best you can do is pick a point in the plane such that the error vector is orthogonal, and that's the principle of orthogonality. Slightly better than Friday. More room, at least. Okay, so if we're working from this assumption that this has to be true for all script L, then we're going to have a whole mess of equations here, right? So we've got one of these equations for every script L. And so what we're doing on slide, I think it's probably slide 10 in yours because I inserted a page, is we're looking at each of these equations for script L. And I think on this page we looked at these two. And those two, I guess I should also mention that expectation is a linear operation. Expectation of the sum of things is the sum of expectations. And so that's why I'm breaking this up into two expressions, because expectation of, say, x minus y times z is the expectation of xz minus expectation of yz. And so essentially what I'm doing is just this guy on this page. Okay. Which leaves the first expectation on the next page. But did anyone have any questions on this page? What we decided was for many of these L's, we get a 0 expectation, or it's a covariance in this case. It's expectation of a product, so it's going to look like a covariance. But for some of the L's, that is for L's between 0 and the delay that we choose, we are going to get something non-zero, and that's going to be the conjugate of the filter at U minus L. The filter tap at U minus L, and again, a channel tap is a value of the channel's impulse response in discrete time, scaled by the energy in the nth symbol. But if we're doing QPSK, the energy in all the symbols are the same. Okay. Okay. So let's talk about the other part of this expectation. So what we've got here, I'm gonna define this kind of helper function as what is essentially an autocorrelation between z and itself. And so what we've got is here, this term is the sum of f of I, z of n minus I. Yeah. And then we're multiplying that by z star. Z of n. Sorry, z of n minus L. Okay, and then maybe the next step that we're kind of missing here is that we're writing the z's as the convolution of the s's with the channel. And so that convolution is here. And coincidentally, here. Add that to the filtered noise. And that's where you get these mega parentheses expressions. Okay, so what we are looking at here is, I see it as a binomial times a binomial. So I think I want to FOIL this. I want to do firsts, and then I want to do lasts, and then we'll do inners, and then we'll do outers. If that makes sense. I think that now that I've drawn all those highlights, they make no sense. So I think I will just instruct you that we are going to do firsts, and then lasts, and then inners, and then outers. So let's do firsts. We're doing expectation of the sum over I of hi s sub n plus m plus I times the sum over j of h sub j s sub n minus j. All right. Well, these are kind of independent sums, right? There's no j's in the I sum, there's no i's in the j sum, so we don't have to do them separately, we can do them together. So this is the expectation of the sum over I and j of hi times hj times the first s times the second s. But the h's are deterministic, so I'm going to use the linearity of expectation and move the expectation operator inside here. So this is the sum of, sum of I and j, hi times hj times the expectation of how s plus m plus I varies with s sub n minus j. Now, we noted that the symbols are independent and identically distributed. We made that assumption kind of up at the very top, which means that if these subscripts are different, then these are two independent random variables. So if n plus m plus I is unequal to n minus j, then we've got the expectation of the first times the expectation of the second, which are both zero. They're both zero mean random variables. So this thing goes to zero. Else, what would have happened? We've got n plus m plus I equals n minus j. Drop the n's. And I think we've got, how would you do this? You'd have I equals minus m minus j, or the other way around. And if that's true, then we get the same random variable squared, which means we're looking for its covariance, which means we're getting its energy. And so what you end up with here is that for most of the i's, there is a whole bunch of zeros in the sum over I. For one of those i's, we're getting something non-zero. And in fact, I may have messed up the signs, SIG ends here. For this particular I, this is the only term in the I sum that is non-zero. Therefore, we don't really have an I sum if we're just adding 0 plus 0 plus 0 plus non-zero plus 0 plus 0. So why even write it as a sum, which is why this sum, the only sum we have remaining is the J sum. Okay, and then this again is the energy in the symbol, which will scale depending on how powerful we make our QPSK modulator. Great, that was the firsts in our FOIL. Let's do the lasts. So here is the firsts. And let's over here lasts. So now we're looking at expectation of W n plus m times W star of n. Well, again, this is a filtered noise process, and we're only doing LTI filtering. So if we started with something that was Gaussian, if we pass that through an LTI system, then the result will also be Gaussian. So my claim is that W of n and W of n plus m are both uncorrelated Gaussians. And so what we get here is 0 if n plus m is different than n, because then we're talking about different time indices, which means we're talking about independent random variables, which means we're talking about the product of their expectations rather than the expectation of their product, which means 0 mean times 0 mean gets us 0. Otherwise, we are looking at the covariance in a single Gaussian sample when n plus m equals n, also known as when m equals 0. And so the way that I'm communicating that is the Kronecker delta, or the unit sample signal in discrete time. This signal is 0 if m equals 0. Sorry, it's 1 if m equals 0 and 0 otherwise. Okay, so I'm encoding this information into this delta. Okay, fantastic. Anyone want to venture a guess about why? I mean, there are only two terms in this last line here, and we've still got the outers and the inners to do in this FOIL. Rather than me spell it out in gory detail, anyone want to take a stab at why we can say, yeah, skip it. It's going to be 0.
Does it kind of involve conditions that we set below, that they would approach 0 if the m plus m plus I does not equal n minus j?
So those conditions were important because we had S times S, or W times W.
Okay.
But in the inners and the outers, we get S things times W things, and W things times S things.
Is W noise again?
Yes, yeah, it's a filtered noise, but yeah, you can think of it just as noise.
Is it because W plus, I'm assuming maybe like W plus N plus, like the two W's, you can, I feel like you can, like the expectation of them are, isn't it to 0 if it's noise? Or at least to a constant, right? I'm not necessarily sure, but I felt like they're like negligible and maybe both the same in some sense because it's by noise.
I don't think there's any kind of appeal to negligibility here. This is mostly just a statistical argument, is that if S and W are independent, remember what this is saying. This is saying that the noise is independent of the symbol and the symbol is independent of the noise, which I think is a reasonable thing to say, then the expectation of S times W is the expectation of S times the expectation of W. Both of these happen to be zero mean for all indices. And so that's why the outers and the inners we can wipe away and say they're all zero. Okay. Any questions on because it's literally waving my hands, but otherwise we're not going to make much progress here. Okay. So what have we accomplished? I think this is what we started with. This was as a result of the orthogonality principle. And what we said was that since expectation is linear, I can take these guys and I can move them to the other side of the zero, or the other side of the equal sign. And we get the second line. And on 2 slides ago, we reduced from here to here. And then on the last slide, we were able to get from, well, if you like, this is that autocorrelation, R sub z, now with an L minus I delay, because you have a total of L minus I delay here. And so that's what we get down here. And then what we did was we said that R of z, we have a closed form for it, and that's this parenthetical. Okay, so this slide is just summary, trying to bring several slides together. So what we've got is, oh, okay. Maybe I should ask you, what do we got? What do we have here? We've got a whole lot of equations, right? This looks like one equation. It looks like a messy equation, but it looks like only one equation. But I want to point out that this is actually technically an infinite number of equations, right? They're all indexed by L. You let L be 0, you get one equation. You let L be 1, you get a new equation. So we get a number of conditions that we need to satisfy. What are our variables here? Like, if I have a bunch of conditions I want to satisfy, what is the thing that I can change to satisfy those conditions? What is our degree of freedom here? Anyone keep their eyes on the overall prize while we're down here in the mud?
Is it U?
U is a degree of freedom, absolutely. So U is a degree of freedom, but it's only one degree of freedom, and we've got an infinite number of equations here.
So then would it be L?
So think about it, for every L, we have one equation. So L, think of it more as a counter, not a degree of freedom. But I mean, I like this game. We're just looking and finding all the letters.
H?
H, let's talk about what H represents. H represents the channel taps. So the effect that our pulse shaping channel and then unpulse shaping has on the symbols. And so because H has the channel stuff wrapped into it, I wouldn't call that a degree of freedom for us as designers.
You can choose the energy of the symbols, right?
We could choose the energy of symbols, but again, that's only one degree of freedom. So yeah, if you like. But also, like, intuitively, if ES is big, we should, relative to the noise, then that's essentially just manufacturing signal to noise for us. If we consider SNR as fixed, then all of a sudden I've fixed script n and I've fixed ES. Is there anything else we can do?
Well, it leaves I. It's a delay in there's a delay in the pulse function, and I'm not necessarily sure where it's used in the subscript of H.
So I out here, we're getting closer actually. You might not believe me, but we're getting warmer. I is kind of like a dummy variable. So it just indexes that outer sum.
I guess what F is? Can we determine what F is?
I think that's the only one left. These are our degrees of freedom. They are, and I'm using that term to mean the variables that we can choose, that we must choose, right? Because at the beginning of all of this, the game was pick an equalizer filter that I called capital F of Z. Now, picking a filter F of Z is the same as picking that filter's impulse response, which is what these guys are. This is our equalizer filter impulse response taps, or impulse response / taps. We have an infinite number of them because at the very beginning I said, let's not restrict ourselves to finite impulse response filters. On the next slide is when we are going to start to restrain ourselves to finite impulse response filters. But yeah, so this is technically an infinity of equations, and we have infinity plus 1 degrees of freedom. How hard could that be? Or I'm not counting actually technically the energy. I'm saying like if we fix the SNR, then that would mean fixing the ratio ES and N. And so then our degrees of freedom are all of the filter taps, so the little FIs, and then the delay factor. But if we constrain ourselves to talk about only finite impulse response filters, then these infinities are going to become finite numbers. Okay, so let's do that. So if I constrain our filter to be FIR, and we'll say whatever that length happens to be, we'll call it capital M. Then the system of equations that I have at the bottom of the last slide can be written like this, where this is the dividing line between L less than U and L bigger than U. So these are for L. This would be L equals 0. This would be L equals 1. And this is for L's greater than U. Okay, so what does this all mean for us? I think it means that we have an M plus 1 by M plus 1 matrix whose entries are populated with the autocorrelation of the noise. Right, that was R sub Z. Sorry, the autocorrelation of the received signal. So this is very much should remind you of kind of a matched filter. And then we've got our degrees of freedom. So these are the variables. And then we've got it set equal to a fixed number, or a fixed vector anyway. this will also be, we'll only take as many of these, as many as we need to make this an m vector, m+1 vector, sorry. And so you're saying, well, what if you don't have that many? Well, remember that U is technically another degree of freedom. And so I think what we're saying here is that if we constrain the equalizer to be FIR, well, guess what? That means that you can't wait any longer than that impulse response to make your decision. Okay, so if the equalizer has an impulse response of length m, then we can't wait any longer than m to make our decision. Does that make sense? Then otherwise, then the symbol at the very beginning of the frame will have washed out of the filter by the time we make our decision. So you're actually just, you're procrastinating too long, which is, I'm sure, something that none of you have ever felt. You end up losing the beginning part of your signal. Okay, so if you have picked your U, then all you have to do is invert this matrix. So invert, multiply it over here, and that gives you your equalizer taps for your FIR equalizer. So when I say, oh, just invert a matrix, what immediately springs to mind as a possible stumbling block here? No? All matrices can be inverted? No problem?
Could you repeat that question again?
Yeah, so I said that in order to solve for our variables, I am going to invert this big old autocorrelation matrix and then multiply on the left by that inverse matrix. And that leaves me with just my variables on the left, and it leaves me with some vector on the right. Job done. Now, that is overly simplistic, and I want you to tell me one of the many reasons why that's overly simplistic. What am I not saying? Go ahead, Sandra.
You have to have the same dimensions for matrix?
Sure, we can only ever hope to invert a square matrix, but luckily, the way this guy is constructed, it's going to be m+1 by m+1. So actually, squareness we've got covered.
Is it something to do with the determinant?
Yes.
Okay.
Yeah.
I sort of remember, but not really. I know it's something to do with the determinant.
Yeah, so what feature do we need the determinant of this square matrix to have in order for us to be able to invert it?
It's got to be non-zero, right?
Good. Anything with a non-zero determinant is technically invertible. And what they don't teach you in linear algebra 1 is that not all invertible matrices are created equal. And that has something to do with numerical precision, which actually kind of gets us back to something that engineers might be interested in, which is not at all obvious when you first take your linear algebra course. And that is, if I want to take the inverse of this matrix, then I am going to need to end up dividing by the determinant somewhere. And that's why we don't want the determinant to be 0. But even if the determinant is very small, so if the determinant of this R matrix is, I'll just use small. We're just doing qualitative terms here. If the determinant is small, then any error that I might have in the entries which are all going to be shuffled around, right? When you do a matrix inverse, you get some arithmetic done on the entries, and then you divide by the determinant. If the determinant is small, then any error in any of the entries is going to be amplified, like the reciprocal of that small number. Okay, so this, if the determinant is small, this is called an ill-conditioned matrix. And for a square matrix to be ill-conditioned, it is sufficient that any of its eigenvalues are close to 0. So this is equivalent to lambda I small for any I. Okay, and so this should be so if your eigenvalues or any of your eigenvalues are 0, that means that your null space is non-zero, which means you can't invert. And you've heard all these words and you're used to just ignoring them, like I was in undergrad. But we can actually take this and say, oh, if my eigenvalue is small, I'm still technically invertible, but I'm going to get a huge size, quote unquote, size of my determinant. And so this can lead to small errors amplifying themselves. So what's to do here? How do we know if we have an ill-conditioned R matrix? Well, remember that the Z's are all comprised of both the sum of the symbols smeared by the channel added to the noise. And so what we would like is to have, what we'd really like is to have a diagonal matrix. Then inverting a diagonal matrix, provided none of the diagonal elements are 0, that's where it's at. So check this out. The diagonal on this matrix is all the same value, right? It's all the autocorrelation at 0. So as long as that number isn't 0, then we ought to be in pretty good shape. And a matrix is well approximated by a diagonal matrix if its diagonal elements are much larger than its off-diagonal elements. Okay, so what we'd like is to have autocorrelation that falls off steeply away from 0. Does this sound at all familiar? This sounds a whole lot like the matched filter, in which when we had perfect alignment, we had a spike in the output of our matched filter, and when we had misalignment, we'd have the response going away down to 0. So everything that made a good communication system back in the day when all we had was matched filters will do the same, will have the same benefits here, right? Like pulse shaping and small noise to signal ratio or large signal to noise ratio. All of those things will make this R matrix well conditioned. And if you lose any of those, you can start getting into the territory of ill conditioned. Questions on this? All right, that was a nice little foray into numerical analysis, in which we actually didn't do any numerical analysis. But perhaps you're thinking, well, wait a minute, what about you? This delay factor. So far, he's been telling me, oh, just set it equal to 0, blah, 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 blah. But I think that you can also see that if I flip back here for a second, that there are only a finite number of choices for you. Once we fix the length of the equalizer filter, then we've only got a finite number of choices for you. It can be 0 up to m. But that means that in principle, we could do this operation. We could do this matrix inverse for each of the u's and then pick the best one. And that's actually what we're going to do over here. So what this would be is basically an iterative process in which we solve the prior system of equations once for every u, and then we pick the one that gives us the least error. Okay, so what we've got here is just a kind of a refresher memory about what all the signals are coming from. And then this is again saying that the error is going to be perpendicular to the data And then what that means is this perpendicularity means that the inner product, so this is the inner product of the error with the, what do we got here? Okay, I see. So if we are perpendicular to the data, that means we're also perpendicular to linear combinations of the data, which is how we get from the z's to the d's here, is because the d's are linear combinations of the z's, because we're doing linear time invariant type operations. So this is our implementation of inner product when we're dealing with random variables. And so what we get here is a whole nother mess of, let's see, what do we got here? Okay, so I guess this is a whole bunch of foils again, where the only one that are remaining are the firsts. So this gets us to the expression at the very bottom, which I think I'm trying to wave my hands around and convince you that again, this is the minimum, sorry, the mean square error as a function of delay is this quantity. And so what this allows us to do is if we solve, so pick u equal to 0, solve the previous expression from the previous slide for f is r inverse times this h of 0 and a bunch of zeros. That'll give you your f's, and that will allow you to evaluate what is the mean square error of 0 by using this formula. Okay, that's one possible result. And now iterate. Now pick u equal to 1, resolve a new system, f equals r inverse of now h of 0, h of negative 1, scrap that, h of 1, h of 0, and then zeros, and then evaluate the mean squared error when u is equal to 1. Keep doing this until you've got u up into m, and what you'll have is 1, 2, ... m plus 1 numbers from which you need to pick the one that gives you the minimum error, or because of this negative sign, the one that gives you the maximum of this quantity. Right? So these f's, I'm saying, depend on u, the time delay u. Can you see how this is useful? Like, if you only have a short number of taps for your equalizer filter, then you do this, what, 2 or 3 times. It also means that your matrix is only of size 2 or 3, which means it's actually quicker to numerically invert. So right, everything becomes easier if you have a shorter filter. However, I think you'll also acknowledge that if I have a shorter filter, that restricts the quality of my filtering, the quality of my equalization. So there's going to be a trade-off here between how much ISI and noise your equalizer can get rid of, and how like physically long it takes to compare all of these options. Because at the end of the day, what we're really doing here is we're making an assumption that the channel is LTI. And that assumption is, when it's valid, that assumption is usually only valid for a short amount of time. Because what I'm not really acknowledging here is the fact that H is going to be varying with time, right? If you're moving in a car, then the channel between your phone and the base station is varying with time. And so what we've implicitly done here is we've assumed that that channel is fixed, but that assumption will only be valid for potentially a short amount of time. And so what we need to do is we need to design an equalizer once for every channel condition that we see. If the channel is static, then we only need to do it once. If the channel is dynamic, we need to do it once every time the channel effectively changes, which is why I'm harping on doing this thing numerically quickly. Yeah. So a more quickly varying channel will require a shorter equalizer filter, which means your estimations are going to be poorer. Everything gets harder if the channel varies quickly, right? Because you have to do everything in a short amount of time, and then as soon as the channel changes, all your effort is wasted, and you have to start over again. Cool. Questions? Could you do this? Could you do this in a homework? Oh, we'll see. All right, we got 4 minutes. Let's do FDM. I want to point out that this whole idea of using filters and all that is not actually all that well motivated, because there is a simpler explanation, a simpler solution for intersymbol interference. And that is, hey, if you've got intersymbol interference, just transmit your symbols less frequently. Okay, you'll take a hit on data rate, but the idea, like this, the basic idea is that if I've got symbols in a long string, so S0, S1, S2, S3, and technically in both directions, we're going to assume this has been running forever. What we've been so far saying is that the next symbol is coming right away after the last symbol, and that is true for every symbol iteration. But if you've got a mess of intersymbol interference, which is usually contributed to by the fact that you have a non-memoryless channel, which is another way of saying you've got multipath in your channel to get from transmit to receive, why not just chill for a little bit, right? So in the extreme, you could send in time slot 0, you could send x0. In time slot 1, you could send nothing. In time slot 2, you could send S1, and then you could send nothing. And then you could do this. Sorry, this would be X4. Right? This should, if I'm actually sending fewer symbols through the channel, then this should be a way to reduce the amount of intersymbol interference. Right? If every symbol takes 2 periods, if I'm allowing every symbol to take 2 periods through, I've halved my data rate, but maybe I have diminished the number of errors I make in decoding. Now, this is kind of an extreme example. Usually how this gets presented is we do something like send a bunch of symbols straight away and then wait. So this would be send symbol 1, then send symbol 2, then send symbol 0, then symbol 1, then symbol 2, then symbol 3, and then wait. And then do symbol 4 here in X4. And then symbol 5, and then etc. So what I've boxed here is what I'm going to call a frame. It's a set of symbols. And what so far we've been doing is we've been saying every frame is full of symbols. But what I'm proposing now is, well, let's take the frame length and allocate a couple of the slots within that frame to just send nothing. And the motivation for this is we've got a channel, it's got memory in the channel, so maybe we should just wait until things get out of the channel. And what we can do is essentially start fresh. Okay, because the idea is that we're going to wait L time samples, where L was the length of the impulse response of the channel. Right, so this is a way to clear the channel of your old messages, and then you can start up again. Okay, is that reasonable? A reasonable way to try to combat ISI? You send a burst, you wait for a bit, then you send the next burst. How long you wait depends on how long it takes the echoes of every symbol to get through the channel, also known as the channel tap length. Okay, so if you're going to pad with zeros, that's one approach, but I think that you might remember from 328 is that padding with zeros, why not just pad with more data? So the cyclic prefix is a little strange. I'm going to actually show it as a suffix, but the idea is the same. X0, X1, X2, X3. And then here, I'll show it as a prefix. What we end up doing is putting the same data cyclically shifted back behind. So then this would be 0, 1, 2, 3, 4, 5, 6, 7. So this will be X7, X6. This would be the next frame. This, on its face, it sounds like we're not giving the channel a rest, but I want to show you Wednesday, that this actually does accomplish the same thing as zero padding. Is what we're essentially doing is we are not putting any new things into the channel. And if I say it that way, then whether we send zeros or whether we send repeated things doesn't actually matter. Okay, and there will be advantages to doing it this way rather than this way. And they have to do with discontinuities and avoiding those discontinuities in the time domain. Discontinuities in the time domain produce widespread in the frequency domain. Okay, so if I can make my signal kind of more consistent here with symbols in every slot, if some of those symbols are repeated, then it has the same effect of letting the channel quote unquote rest between frames. Okay, you've been troopers sitting through this. I will hold on a second.
Yeah, I'll let you.
Thank you. I don't think I'll have a full lecture worth of OFDM on Wednesday, but I have linked to a lecture on OFDM by another instructor that I'd like you to watch, and maybe we can discuss it in the bulk of Wednesday's class that we don't have stuff to talk about from the slides. Okay, so your participation in Unit 5 will be watching those videos by a guy named Irfan Ali, and they're linked on Canvas right now. Please do that before we get together on Class Wednesday. Okay, Andrew, question.
Does the wait time depend on how long your frame is in the zero pad? Is that something that you would have to necessarily look at? I don't know if that.
So yeah, so I picked 0, 1, 2, 3, and then a wait for 2. Both of those are design parameters. The wait length is dictated by the channel memory.
Okay.
But the fact that I just did 4 symbols, that's another design parameter. So
Okay.
you would also think that you could get a better efficiency if you increase this number relative to this number. That way you're sending more things per time on average.
Okay, that sounds good. Thank you.